Okay, in this video, this is going to be the second part, sort of the tag along for analyzing a circuit. And in the first video, I went over Kirchoff's laws, so if you haven't had time to look at that, I would look at that video first because this one will make a lot more sense. Okay, so the first thing we're going to do is read the problem here. It says find V2, which is right here, in the circuit diagram given that the 1 ohm resistor has a current of 2.6 amps flowing through it. Okay, so first thing we need to do when you're analyzing this circuit is look at your givens. And your givens are going to be the G part of the guess method that I use to solve problems. And we're going to find that we have a lot more givens than we realize once we go ahead and label our circuit diagram. So the givens, we're going to draw our circuit. And then we are going to label our currents, our resistors, which we've already done. We're going to label our junctions. We're going to label absolutely everything, right? Our batteries, we're going to label everything. All right, so let's do that. So let's label our junctions. We have a junction here and a junction here. And then we need to label our currents. You want to label the currents. Oh, did I put that in here? Label current. Okay. So I'm going to have our current coming out of this junction going up this way. We're going to call this I1. I'm going to have a current coming out of this junction. I'll call that I2. And then we'll have the current coming this way. We'll call that I3. Now we have to follow Kirchoff's laws that I went over in the first video to be able to do this. All right, so after I've labeled the currents, then in our junctions and our batteries and all that, we're going to be down to this part of the guess method, which is our unknowns. So we are going to look at every single thing that we've drawn, and we're going to determine what we have values for and what we don't. Well, our problem said that the current through the 1 ohm bottom resistor is 2.6 amps. Well, that current is I1. So we know now that I1, no, that's not an unknown. That's going to be, we'll put that up here because that's a given now. I1 equals 2.6 amps. So we can put that on our circuit diagram as well as being I1. But our unknowns, well, let's see what else we drew. We drew I2, we don't know I2, and we drew I3, we don't know I3, and we are looking for V2. So that is three things we don't know. We don't know I2, we don't know V2, and we don't know I3. Okay. Now we need to count our unknowns. So we have three unknowns. And this is important because we're going to need three equations. So however many unknowns you have, you're going to need three equations to solve. And that's fine. Equations is our next step because we're going to use Kirchoff's laws to get these equations. Okay? All right, so the very first law is the junction law. And using the junction law, we know that the sum of the currents going into a junction must equal the sum of the currents coming out. We'll call that junction A. We're going to call this junction B. So for A, what that looks like mathematically is I3 is coming into the junction and I2 right here and I1 are coming out. So we'll have that equals I2 plus I1. Now we also have the junction B that we can analyze. And the currents going in, oh, stars. There we go. Thank goodness for undo buttons. Okay. we have the currents I2 and I1 going into B. So we're going to have I1 plus I2 equals the sum of the currents leaving B, which is I3 right here. Okay, but these are basically the same equation, right? They're not giving us any new information. So since the equation isn't giving us new information, we can only count one of these, so we'll count this one as one of our equations. Okay, let's get a little bit more room. Now, since we've used the junction law, now we're going to look at using the loop law to get some equations. Well, the loop law says that within any closed loop, the sum of the voltages must sum to 0. So this is going to be a closed loop, and this will be a closed loop. So we'll say this loop up here is going clockwise. Call this L1. And you could go counterclockwise if you wish, but I just like clockwise. And then down here, I'm going to make it go clockwise as well. We'll call that L2. All right, so let's look at L1, knowing that they all sum to be 0. And starting here with our analysis of loop 1, we go around and we end up at a 30 ohm resistor. And we see that we have the current going through the loop, or going through this element of our circuit in the same direction as our loop. And because it's going in the same direction, we're going to subtract it. Subtract the voltage. So we'll have the voltage times the resistance. Okay. Now we're going to keep going around here. And there's nothing else to analyze on this part of our trip around the loop. But then we get to this negative end of the battery. And because the loop is pointing in the direction of this negative end of the battery, we are going to add the voltage that's found at this end, which is going to be 45 volts. All right, and then we're going to keep going around, and now we come to a 1 ohm resistor. Well, this time the current is flowing in the same direction as our loop, and so we're going to be subtracting our voltage. So we subtract V times 1, and then we keep going around, and we're going to come to a 40 ohm resistor where the current is still going in the same direction, so we will be subtracting minus V40 as we continue around and around the loop, and then we're back to where we started, and we've analyzed everything. Nothing else to analyze, so L1 has been completely analyzed. Now, if we remember from earlier physics classes that voltage, I'll put this up here in the corner, voltage equals IR. And the reason that we do these circuit analyses is so we can find the individual current going through each element of our circuit. And so if we look, we have V right here in each of these, and we already have the resistance. So what we can do is we can sub in current. So if when we're going around right here in our circuit, this current that is flowing through this 30 ohm resistor, we have labeled as I2. So we're just going to switch this out for I2 and leave that 30. And this I times R is voltage. Let's do that, and we leave the 45 volts alone. And then we're going to go to the next part of our circuit that we analyzed, which is our battery, which we left alone. And then we go right here to this 1 ohm resistor. Well, this current we labeled as I3. So minus I3, 1. And the same for the next part. It's going to be minus I3, 40. Okay, then we are going to look at this. So this is going to be our substitute part of the guess method, where we start subbing in things. And so we're going to see that I2 is by itself. We only have one of those. We have one 45 volt, but we have two I3, so we can put those together. And the way that we do that is we say, let's go ahead and copy this as it is. But we have two I3s. We just take I3 out, and then we add the resistance. So we have a 40 and a 41. We just add those. Equals 0. Now this is new information, so it counts as an equation. So that is our second equation that we'll be using. All right, so now let's go on and let's analyze loop 2 right here. And we'll start in this left-hand corner. First thing we come to is a 40 ohm resistor. Now this 40 ohm resistor this time is going in the opposite, our loop is going in the opposite direction as our current flow. And so because we're going in the opposite direction, according to the loop law, we need to add this. We're going to add V40 plus, oh, let me not plus yet. Okay, then we're going to go around and we hit a 1 ohm resistor. And this 1 ohm resistor is also having current flow through it that is in the opposite direction to our loop. So we'll be adding plus V1. And for this, I'm going to put a VT for top because you see, we also have a 1 ohm resistor on the bottom. So just to differentiate which one we're talking about. Okay, and then we're going to come to this battery. Well, this time the battery, or the loop is pointing at the positive end of the battery. And so we're going to subtract this voltage. So subtract 45 volts. Then as we come around, we're going to hit a 20 ohm resistor. Well, now our current is flowing in the opposite direction. I1 flows up and L2 is circling around. So this is the opposite direction. So we're going to add plus V20 ohms. Okay, and then we're going to come down here. And now we're at a 1 ohm resistor at the bottom. And our current is still flowing in the opposite direction. So we're going to add V1. Put that VB for bottom. And as we come around, our loop is pointing at the positive end of our battery. And so therefore we're going to subtract this voltage here, which we don't know yet, minus V2. And then we continue around our loop and we realize there's nothing else to analyze. So we're done with this loop. So now let's go ahead and substitute, clean this up a bit. Okay. So starting at the top, we see this subtracted voltage that we're doing has a current running through it of I3 for both the 40 ohm and the 1 ohm resistor. So we can say plus I3 40 plus I3 1. Our voltage that we come to right here from our battery, that stays the same because that's not based on, we didn't label that based on how the current was flowing, remember? That was only based on if the direction of the loop was pointing at the positive end or the negative end. It had nothing to do with if the current was doing that in reference to the loop. The current is only referenced with respect to the loop when it has to do with other aspects of the battery, such as the resistors and things of that nature. Okay. So we've subtracted 45 volts. Now we come to the 20 volts and we realize that that has the current of I1 going through it. So we can say plus I1 20. And then we go down here and we're at our 1 ohm resistor, and that too has I1 going through it. And then we have our minus V2, which stays the same. And then we were done. Okay. So then let's clean this up. have I3 and I3. So we have two I3s. So let's do I3, and then we add these together, the 40 and the 1. So we get I3 41 minus 45 volts. And then we have two I1s right here. So we have I1 minus I1. Oh no, that's a plus I1. 21. So we're adding the resistors right there. So 21. And then minus V2. And if you see here, we can just bring V2 over to the other side, because that's one of the things that was on our unknowns. And so we've already got an equation to solve for that. Okay, so now we have three equations. And so now we can go to the last part of our guess method, which is to solve. All right, so the very first equation that we derived from the junction law was I3 equals I2 plus I1. Well, if you look at our second equation, we have two unknowns here. We have negative I2 and we also have negative I3. But we've solved for I3 up here, and if we plug that in for this I3, then we can make it to where we only have one unknown and we can solve for that unknown. So let's do that. Okay, so we have, let's do negative I2 30 plus 45 minus I3 41 equals 0. And then we're going to sub in, so let's do minus I2. Actually, I'm just going to sub it in right here instead of rewriting all of it. I'll do it in red. Minus, and then we're going to plug in I2 plus I1 times 41. Is that what that was? Yep. Because we're plugging this in, this right here, for I3 in this equation. All right, then we need to distribute that. So we'll have minus I2 30 plus 45 minus I2 41 minus I1 41 equals 0. And this became a minus because I distributed that minus sign throughout. Okay. So now we can fill in some things that we know. And we know that I1 is 2.6 amps. So we can fill that in. And then, let's see, we also have 45. And we can combine these I2s. So we have minus I2, 71. Do you see that? So we have this 30 and this 41, so we put them together. And so now what we do is we say minus I2 times 71 equals, we'll have 2.6 times 41, so I just plus this over to the other side, right? And then I minus the 45 over to the other side. Okay, so let me put that in the calculator. And this is going to equal 61.6. And then we have negative I2. So we're going to just switch that negative around. We're going to just, what we can do is we'll say divided by negative 71. We'll do that. So we have 61.6 divided by negative 71, and I2 equals negative 0.867605633803. And in our problem, we were only given two significant figures. So if you were asked for just this, it would be 0.88 amps. But when we're doing our calculations, we want for everything to be exact as possible, so we'll leave it as that. Now, this negative sign. This is why it doesn't matter if you draw your currents wrong, or not wrong, but just different. You're gonna have, you see how we drew our I2 current as going this way? Well, if we got a negative mathematically, that's just letting us know that, you know, IRL, in real life, the current is actually going this way. But we're not going to change our mathematics because we've set up everything to account for I2 going this way. But it just lets you know. So it's really no big deal how you draw it as long as you're following Kirchoff's laws. Okay, so now we have found I2. And now, if you see up here, we have this equation that says I3 equals I2 plus I1. Well, we know I1 is 2.6 amps, and now we know I2, so we're about to know I3. See how that works? So we have, we have I3 equals I2, which is this that we just found, plus 2.6. And that equals 1.7323943,662, which is approximately 1.7 amps for I3. All right, well now we only have one thing left that we need to find, and we also have one more equation. So now if you look here, this is the equation that we'll be using to solve for V2. So now we'll go down here. We have V2 equals I3, which is what we just found. So let's plug this in. Times 41 minus 45 volts plus I1, which we know is 2.6, times 21. Okay. And I get that V2 equals 84.62. There we go. Volts. And we should have it at, 2 sig figs. So that's about 85 volts. And there's a big difference when you round early. I just looked at a problem. I did this problem earlier, and I rounded really early, and it left me with 80.612 volts. So it makes a huge difference when you round, a huge difference. So make sure you're not rounding until the very end, so that way you don't get things wrong. All right, and my biggest advice is to practice. You know, take this and do this problem and try to maybe explain it to someone else, and you'll be well on your way to understanding how to confidently analyze a circuit diagram.